Thank you so much. All right.
All right, well, thanks for having me, guys. Mr. Bango gave me a pretty good intro there, but I did go back to some of the old yearbooks to dig up some good material for you guys to show what it was like back then. So yeah, it was class of 2007. Our motto was "License to Chill," which was pretty cool, going on the 007 theme there. Few teachers I had, see Mr. Brennan, took physics with him. I think contemporary physics was the last class I took with him senior year. Mrs. O'Connell, Mrs. Lassard. I think that picture of Mrs. Lassard is actually from a middle school yearbook I had. So definitely hold on to those things. They're pretty funny as you get older. So a few pictures of me. Bottom right was my senior photo. I think that's a puka shell necklace. Maybe not. Don't hold me to that. But yeah, I think, in high school, a lot of my interests were certainly on the math and physics side. I really liked some of the computer science classes I took. I think Lynn Fisher was teaching those back in the day. And but I really didn't know what I wanted to do. I wouldn't say I had any career goals. I really liked animals and biology as well. So I was kind of open to that as a career path. And I'd say skiing was probably one of my favorite things back then. It's hard, I think, at that point to call something like math or physics your passion necessarily, or understand how that relates to a career path. So, but I was pretty open to a lot of different things. I knew at the time I wanted to go to college and kind of try to figure that out. So I think going to Woodstock certainly set me up well for that. And I think especially, you guys probably have access to this too, but the computer science stuff was really helpful going through college, because one of the first courses you had to take was Intro to Computer Programming as an engineer when I went to school. And that class was a breeze because I'd already taken computer science in high school. So all those skills of being able to do simple coding things, script things for data analysis is helpful in pretty much any technical field you go in, even if it's something like biology where you're going through a lot of data analysis or something like that. So applied to a bunch of colleges, got into a few, and ended up deciding to go to Tufts University, which is in Medford, Massachusetts, right outside of Boston. I wasn't really sure what I wanted to do, but I knew I should probably go to school that had engineering in case I wanted to go down that path. I actually was accepted into the liberal arts school at Tufts and started out as a bio major and then switched to engineering school freshman year. I found some of the bio classes I took just weren't quite as engaging as the engineering courses, where it's not a totally fair characterization, obviously, to biology, because there's a lot of really cool research and set of experiments that you have to do in biology. But I just felt like the engineering was a little bit more like active problem solving to me as I was learning it. And I just enjoyed it. And typically it's easier to start in, like, if there's a school where you could either do engineering or not, it's easier to start in engineering because a lot of the requirements are a little tougher, and it's harder if you're not on that track to get back on it later on without missing time. So in the world of engineering, there's a ton of different kinds, right? And I really didn't know much about any of them. And I have a few down here. I don't know how familiar you guys are with different engineering disciplines, but here are a few of the bigger ones I was considering. It's certainly not an all-inclusive list, but there's civil engineering, which is kind of big structure, bridges, roads, like kind of infrastructure type projects where you're working with, big material properties like concrete and steel, and you're designing things, for infinite life, right? They can never fail. Environmental engineering was kind of interesting to me, especially, growing up in Vermont. I think we all think about the environment quite a bit compared to potentially other states and kids who grow up elsewhere. So, a lot of that work ends up being, water treatment type systems or pollution monitoring. Tufts has a pretty good environmental engineering program, and they'll do stuff like monitor pollution on the I-93 tunnel from the Big Dig and stuff like that, and see how it's affecting, or even look at, for example, pollution from the airport and how it's spreading to nearby communities and stuff like that. And then also, hydrology in terms of how do you build a dam? There's kind of some overlap with civil engineering there, but how you work with the water and you design all the parts of the dam to handle the water and stuff like that is kind of part of environmental engineering. And then electrical engineering, I took a couple classes on that, and I did fine in it, but it was just always a little too abstract for me. But that's a lot of circuit board design, power systems design, right? Like, how do you design a motor, and how do you turn that motor, and stuff like that. It always kind of seems like a little bit of black magic to me still, because it's kind of a cool field because it really is like a human made discipline, right? Like all the ways resistors and circuits work and how you simplify those is really a man-made thing, which is kind of cool. And at Tufts, there's other things you can do, software engineering, if you really want to focus on coding and how do you architect large pieces of software, chemical engineering, if you want to go into, pharmaceutical industry, that's a big one. Or I think a couple of my classmates who are chemical engineers got offers from like Budweiser, for example, to go work at some of their big facilities in large scale beer making and stuff like that. And then biomedical engineering is another kind of tough one where you have to take a lot of the pre-med courses in addition to all the other engineering courses. And that's one where you're looking at, they would go in and try to do like interesting types of like tissue repair and stuff like that, where you take kind of an engineering approach to the biology, pacemakers and stuff like that would certainly fall in that category. But I ended up picking mechanical engineering on the far left. And I think part of it was it's kind of it's a very tangible type of engineering. It's a lot of hardware and physical parts. And if you like things like robotics, that's kind of a confluence, a lot of aspects of mechanical engineering. So you can design the parts for it. You can design the control systems to make all the parts move effectively and make them move in a stable way. The other part of it that I liked, and we'll kind of get into, is fluid dynamics and fluid systems. So how does air or water move, and how can you control it and make it do things that you want? For example, make a plane fly. And another big aspect of it is materials. So what, like advanced material properties, how do you come up with new materials, analyze those? And, especially in the aerospace where we're always looking for really lightweight, really strong materials and figuring out how much we want to pay for those for complexity and cost and stuff like that. So that kind of, I got onto this mechanical engineering track off the bat, and a lot of the intro courses are kind of okay. They get much more interesting as you go on and you start taking more specific classes, I guess. And one cool thing I did in spring of 2010, I studied abroad in Hong Kong. And I would recommend, if you have an opportunity to study abroad, definitely do it, because you really don't have many opportunities to go live in another country for a few months and come right back into the world you were in. And Hong Kong was a pretty interesting experience. It's a really cool place, and actually really cool like hiking and stuff in some of the islands around there. And it's a really safe, big city that you can go live in. And we did a lot of trips into mainland China, Beijing and Shanghai and stuff, which is pretty cool. And while I was over there, I took a bunch of engineering classes to stay on track with my curriculum. I took one interesting one that was failure analysis. So this guy was he's like an engineer that would get called into court when there would be huge, like big, like industrial disasters, like huge machines would break, or even, elevators would malfunction and stuff. And he would get called in as a witness for a lot of this stuff. So the whole class was basically case studies on different failures. And the test would be like, he'd give us this failure of there's something like from a big cement mixing factory, it's like a huge steel roller, for example, and they'd show that it had just sheared in half and rolled through a wall of the factory. And so for the test, you'd get pictures of this failure, and you'd get pictures of the shaft and how it failed. And you'd look at the way the metal failed and try to figure out whether it failed from a large force or fatigue or something like that. And that was a pretty cool class. The one that kind of got me on my current path was a class called aeronautical engineering, which was basically a high-level overview of how you design anything from aircraft engines to aircraft in general, sizing, performance of aircraft and stuff like that. And something about it was just interesting to me. It seemed really challenging, and it still seems kind of crazy that planes can fly. The whole concept of lift is just a pretty interesting thing. So I came back from that junior year and decided I want to try to get a job into aerospace. So I basically started taking and continued to take a lot of classes focused on like fluid dynamics, again, kind of how air moves and water moves. I took a wind turbine design class and stuff like that. Power generation class was really interesting. And then at the same time, I also decided to stay on at Tufts and do a master's program. So they offered basically a 4+1 program where you can get your master's degree in just 1 year. And you basically start doing research for that degree during the summers prior to your junior and senior year, prior to your senior year, and then the summer after. So that was pretty nice, because you definitely, the cool thing about doing grad school work is you get to get a little bit more into the research side of things. So you kind of get to come up with a problem in a lot of cases that's pretty unique, and it's not clear what the solution is, and you have to formulate that. And this one I did, ended up doing research on basically a bird feather like attachment you can put on plane wings that helps them maintain performance after stall. So basically, any wing, if you get it to a high enough angle and airflow, eventually the air can't stay on it anymore and it detaches and you lose a lot of your lift force and it creates a lot of drag. So it's really hard for the engine to keep up. And it can be dangerous depending on, what flight condition you're in. If you're close to the ground and you stall one wing, it can be really hard to recover. And that's a lot of aircraft accidents that will happen like that right after takeoff in small planes if you're not careful. And it depends on the plane design, of course, too. So this was kind of cool when I have some pictures of it down there, but basically this was all done in a wind tunnel, which basically is a huge fan that blows air through a rectangular cross section. You can basically simulate different flight conditions that way. So you can put a wing in there and put it at different angles, measure the forces on the wing. And then what I would do is I would put these flap-like appendages, like super simple, like thin plastic film, and cut it into different shapes and stuff like that. And basically try to simulate what you see on the bottom right there, which birds will do. And basically what happens once the wing enters into stall and the airflow tries to detach, their feathers actually pop up and create these pockets on the back of the wing. And what it does is it kind of helps control the circulation of the air around the wing and actually helps them maintain better lift. And it's pretty sweet. Like if you go to the beach and you watch seagulls, if it's really gusty, you can see this. You watch the back of the wings, you'll see their feathers ruffling, and that's basically their wings stalling and then maintaining much better control than we can on any conventional aircraft. So it's pretty cool. There's a lot of really interesting things in nature that happen like this. And that was kind of, the start of, I ended up doing at some subsequent jobs work on similar type ideas where we were trying to take ideas from nature and apply them, particularly on the small, like drone type scale, to help with control in these really challenging environments like gusts and stuff like that. Sorry, go ahead.
That's biomimicry. The term for that is biomimicry.
Yeah, exactly. And bio-inspired engineering is another one. But there's a lot of cool stuff out there that we're always trying to do. And it's amazing, like watching, what birds can do. It's, we haven't come close to doing anything like that with drones or anything. So the other cool thing, so this is kind of a good example of how our research can go all over the place. So I actually ended up building a force sensor. This is this thing in the bottom left here. And basically it's a piece of machined metal, and there are strain gauges on it that basically measure the deflection of the metal and how much strain is in the metal with different forces on it. And if you arrange them and calibrate them correctly, you can actually pick up all the forces of interest. So you can get your lift force out of it, your drag force, torques on it, and stuff like that. That was a pretty interesting part of it where, I was kind of interested in the aerodynamics, but it ended up being a big hardware and software effort and some electrical engineering there, right? Like integrating that with a data acquisition system and calibrating everything. And that's the thing I kind of like about research is you get to go on these tangents and you don't know exactly what's going to happen. So that all went pretty well, and I graduated. And my first job out of school was at GE Aviation up in Lynn, city of Sin, outside of Boston here. So I actually lived down in the West End, and so you can, when you're coming down the highway, you can see some of those tall white buildings on the right. I was living in that with a couple of friends from school, which was really fun. And I would commute out to Lynn and work for, basically a lot of the work they do is on helicopter engines, but they do some like aircraft engines as well, or plane engines as well. And it was a good first job out of school that they do a lot of work in trying to like train you and help you understand a lot of what's going on. And I worked for them in the performance group, which is basically looking at, how does the engine operate? Is it creating as much power as we want it to? Are the temperatures inside the engine appropriate? And we would even like every engine that was made would go through a test cell, and you'd pull all the temperatures out of it, and you could check them against all these other history of engines and make sure there weren't any outliers in terms of some of the sensor readings. So it's pretty cool. It's a pretty big like data analysis problem. And then you'd see things like, oh, the temperature in this stage of the compressor looks a little funny, or in the exhaust looks funny. And it was amazing. You could actually trace that back sometimes to very specific problems in the engine just by data and sensors and the experience a lot of people have been there. So that was pretty cool. And then after a year, I moved. Basically, they offer rotational type programs. You can try a bunch of different things. And the second year, I moved into the turbine aerodynamics group, which is kind of what I thought I wanted to do at the time. And basically, it's a lot of designing the blades. And I kind of have a little cross-section view here of some of these blades that go on the turbine side of the engine that are extracting energy from the engine cycle. And so a lot of it is doing design of these little blades and making them the right shape and doing very specific shaping near the roots of them to try to limit how the air rolls around them and make sure you don't get some inefficiencies, especially under certain flight conditions. And that was pretty interesting because it was very much like aerodynamic design focused. It did feel a big company like that. To me at least, it felt a little pigeonholed in terms of what you did. Like this was basically, I worked on, single blade design of a certain engine for months and months. And all the design process is kind of laid out already for you from people with PhDs like 10 years ago and how they design these and best practices. So on one hand, it was a really good learning experience, but it felt kind of like, when you're doing these designs, they were kind of incremental improvements. It didn't feel like the innovation that research had felt to me before, where you're doing something really new and exciting. So it was a great experience, but after a couple of years, I decided I wanted to get more into the research side and look at kind of new types of aircraft and new technologies that haven't been done before. And I started looking around in the Boston area. And I found a job at Aurora Flight Sciences, which was in Cambridge. So this was a pretty big departure from GE, where Aurora at the time was a pretty small company, like under 500 people, where GE is like thousands and thousands, right? And just GE Aerospace is thousands and thousands, not to mention all the other GE healthcares. But Aurora is kind of a cool engineering research-oriented company. They've been around since 1989, I think. And they do a lot of like new aircraft configuration stuff and a lot of mostly government type contracts, but it was pretty cool because it really it really gave me the opportunity to work on brand new configurations, things that you'd be working on that you actually weren't sure if they really could be done or not, which is pretty interesting. So some of the projects I got to work on, this top right one is called the Lightning Strike aircraft. Didn't end up getting built, but it's a turbo electric vertical takeoff and landing aircraft where there's actually a helicopter engine in here from, I don't know if you guys are familiar with the Osprey, the big tilt rotor guys, but there's an Osprey engine in here and it's basically turning a generator that then turns all these fans electrically all in sync. And so it's a pretty cool idea. And there's some interesting things that happen in terms of losses that make it pretty efficient. And the idea was to be able to hover and then cruise at over 200 miles per hour. So I did some work on this, doing like internal flow analysis in the wing. Basically, there's a lot of high voltage, hot electrical cables in these trying to run all these high power fans. So I did work analyzing airflow that would get pushed into the wing from these fans and seeing if we could keep all the conductors cool enough. And also did some work looking at thermal stuff in the engine bay, making sure that wouldn't overheat as well. So that was kind of interesting. This thing never ended up getting built. Or actually, it was a partnership with Honeywell, who's making a big generator in here, and the generator actually ended up not working. And it was pretty interesting. There's actually some there's a little bit of misrepresentation of data that ended up coming from them. So that was kind of an interesting lesson in on intellectual honesty, and how it can really impact programs if you don't make the necessary steps early on. This guy down here is a really cool concept called the D8, and it's basically a new type of commercial aircraft that NASA a while ago put out a call to ask about what type of configuration changes can we do for aircraft as opposed to the normal tube and wing aircraft that you guys all fly on that can have immediate fuel savings with current technologies. And this is one of the concepts that came out of MIT, and Aurora was working on quite a bit, and I got to do some work on it as well. And it was pretty cool. It was like 30 or 40% fuel savings as compared to a Boeing 737, which is, if you think about how many of those regional aircraft fly and how much fuel that is, that's a massive impact on emissions if you could do something like this. And it's cool. It's kind of like a wider fuselage, and you basically put the engines on the back of the aircraft and you kind of embed them So as air flows over the top of this thing, it slows down and creates something called a boundary layer. And then the engines actually take that air in and ingest it. And you get a lot of efficiency benefits, both on the engine side, because the engines like to work with slower moving air. It makes them more efficient. And also on the aircraft side, because by ingesting that slow moving air that's coming over the top, you actually help reduce the overall drag of the vehicle, which is kind of cool. So on this guy, I did some work on like the aerodynamic design of some of the fairings up here, looked at some of the engine nacelle profiles and how those should be designed. That was pretty interesting. And then I did a fair amount of work on a few small programs that were more unmanned aerial vehicle or drone type systems. So we would go out and fly these smaller, this is a, I think this is an AeroVironment drone, but we would go out and fly some of these small guys, and some of them were hand launched. So you'd be throwing them in fields nearby in Boston that we were testing. And we did a lot of work. And this is where the bio-inspired stuff kind of came back in, where we did work on advanced sensing technologies for the wings. So another cool thing birds do is they can feel, like as the air changes over one wing, they can feel that and make adjustments in real time. And the way, I don't know if any of you guys have drones or flown drones, but the way drones work is they have all their sensing in here, right? And they sense their rates and their accelerations at their center of gravity and use that to change control. So if you can sense things on the wing as they're happening before it actually results in some type of rate or acceleration on the body of the aircraft, you can potentially react faster and do things like have much better control in gusty conditions. Especially for these small type aircraft that really get like blown around a lot. There's a lot of challenges with them. So I worked on a couple programs there and got a little bit into some of the program management side of it, which is kind of how you deal with the customers, which in a lot of these cases was the Air Force or the Army. So you'd make sure you're meeting your contractual deliverables, you make sure technically you're on track, you're making sure the people working on the program are doing the right work and they have enough bandwidth to help you actually succeed and meet your deadlines. And some of it even obviously gets into the financials and scheduling side of it. So are you burning too much cash too quickly? Do you need to extend the program based on lack of resources internally and stuff? So that was kind of interesting. It's program management is a little bit less technical on the engineering side, but it's cool because you kind of get to drive and lead programs and help them succeed just from a more of a logistics point of view. So yeah, so I really liked this job at Aurora, and it was cool working, right in Kendall Square. It's a pretty awesome place to work, and I would bike to work when I lived in Cambridge, kind of nearby, and that was really fun. But after a while, we decided, my wife and I decided we want to move back to Vermont. We're both from Vermont, and as fun as it was living in Boston for, I think it was like about 10 years, including school, I had a great time. But at a certain point, I think you guys all know how awesome Vermont is. And we would do a lot of trips up in the summer to go mountain biking or skiing in the winter. And we just kind of wanted to move back and get out of the city. So that's where my current job came in. And it was one of those very, it was a really lucky timing kind of thing where I was looking for jobs up here. Wasn't getting a ton of traction, didn't really think I could do aerospace research anymore. So I was looking at other types of jobs. And this company, Beta Technology, just happened to be starting that year. And I actually had been interviewing at a couple other companies for a while. And one of them I thought I was going to get an offer for. And then they had a big hiring freeze, like one of their biggest government programs got paused, so they couldn't hire anyone. So at that point, my wife had already moved back up here and taken a job. And I was basically couch surfing in Boston, still working at Aurora and applying for jobs up here and hoping to find something because I didn't want to take a lot of time off. So one thing led to another, and I got connected to Beta. And at that point, they were about 9. I think I was the 9th employee, and they didn't really have a the company was really founded, and our core strength is really like all the electrical stuff. So from batteries through inverters, all the wiring, motors. And so they didn't really have like an aerospace type background person. So I was a pretty good fit for what they needed at the time. And I came up and started working on electric aircraft specifically. And so the top right one is the first aircraft we built called Ava. And it's basically a modified Lancer aircraft. So it was a normal aircraft that we bought from a company, and we just totally changed it. We chopped off the nose and made it longer. We put these long articulating booms on it with propellers. So there are 8 propellers on it and then a wing in the center. So it kind of flies like a small drone, but at the time this was about 4,000 pounds. And basically we used it as a test bed to try out a lot of different things and a lot of different types of configurations. So how hard is it to tilt propellers and fly an airplane like that? And it was basically using all off-the-shelf components, motors you could buy. And by going through that, we learned a lot, and we got kind of the respect of some of our early investors, and that enabled us to raise more money and go after the current aircraft we're designing now. So this is the bottom right is the aircraft we're working on now. It's called Aaliyah, and it kind of from above, it does look a little bit like a drone, right? There are 4 propellers in each corner, and the goal of this vehicle is to be able to take off vertically like a helicopter. And then you use this pusher propeller on the back to start moving forward. And as you start gaining airspeed, you can start bringing down your lift propellers and eventually get on wing and fly like a normal airplane. And the benefit of this compared to a helicopter is, that the energy and the power required to just stay stationary, hovering in flight is tremendous. And so for these aircraft, if you can get on wing and use a wing to generate lift as you're flying from one place to another, you can save a lot of energy and go a lot further. And that's kind of a key element to a lot of the electric aircraft right now is that the battery energy density is just at the point where a lot of these missions are viable. And so we can start using aircraft like this, which are totally brand new configurations. They don't look anything like a normal helicopter, but they can start to take over helicopter-like missions, which is pretty cool. So this is our, you can see our office. If you ever come up to Burlington and are going to the airport, we're right before the airport. All the actual terminals are kind of up in this area here. But we started across the airport in like a small room with no windows, and it was pretty fun. I hadn't worked at a startup before, but you basically do a little bit of everything. Like I would be hand laying up carbon fiber propellers, like big 10-foot propellers, and I designed some of the landing gear on this as well. And I would do some of the propeller performance analysis and some of the aerodynamic stuff. So it was kind of fun. You did a little bit of everything. And it was really hard. Definitely outside of my comfort zone on a lot of stuff, and made mistakes here and there. One of the biggest ones I made, which was pretty fortunate, is I was designing basically a terminal block for the batteries in this aircraft. And basically in this big, long, ugly nose of this thing, there's a bunch of batteries that help power some of these propellers. And I was designing basically the interface between the high voltage wiring and the batteries. And I made this basically a 3D printed part with metal lugs that I thought would work, and it would simplify everything, and it cleaned up the wiring really nicely. And the mistake I made was I clamped the metal lug around with a bolt around a piece of 3D printed plastic. And in hindsight, it's kind of obvious, but if you have something that's heating and cooling, and it's something like a 3D printed PLA or whatever, that thing's going to deform and change shape. And so what happened was that whole clamping force started to deteriorate, and there started to become a gap between the metal lug and the high voltage wire. And whenever you have that much voltage and current and you start getting a gap, you start arcing. And so we were hovering this thing and put it down, and then we started seeing smoke coming out of the front. And I don't know if you guys seen videos of Teslas or any of the battery fires, but they're really hard to put out. You can just basically dump water on them, and you have to let them do their thing. As we saw smoke coming out of the front of this, and this guy Cam, who does a lot of the operation stuff, drove across the airport like 100 miles per hour in his truck with a fire extinguisher, just dumped a bunch of blew the fire extinguisher inside the nose and put it out. But luckily the fire didn't get to the batteries or anything. And people were well clear of the aircraft at that point. But that's it's a good example of, like, if you're trying to move fast, simple things can kind of get through the cracks if you don't have good review with other people on the team. And I certainly wasn't the only one that looked at it, but I felt that was kind of a tough one to come back for. And I was pretty careful about a lot of designs in that area from there on out.
Hey, Riley, just to interject something. You said when you went to beta, you were like employee number 9. Mm-hmm. Well, and how big is beta now?
350 right now, roughly.
And that's been over how many years?
For about 4 years now. Yeah, so that's been pretty wild to watch. It's changed a lot for sure. We have, a lot of the people, I kind of go into like the different type of people that work here, but when you designing a prototype that flies around Burlington, or we fly a lot over at Plattsburgh Airport across the lake because it's a really nice long runway and there's a lot less traffic. But designing something to go hover and fly around there is one thing, but then designing something that you have to go certify with the FAA that is going to be flying, a lot of flights over urban environments, potentially with passengers. It's kind of a whole nother level of substantiation in terms of how you prove your analysis is safe. So there's been a ton of hiring going on in basically getting us to that ability to actually certify an aircraft. And the other part of it is manufacturing, like being able to manufacture, ideally, and what we'd like to do by the end of this decade is be manufacture like hundreds of these a year. So setting up a facility that can assemble those in Burlington, get them checked out and flight tested over in Plattsburgh, and then shipped out to customers is a huge operational burden that requires a lot of planning and looking at assembly lines and stuff like that. So, yeah, I'll talk a little bit more about these electric aircraft, these eVTOLs, because they are kind of interesting. I think you guys are obviously familiar with electric cars, and there's certainly a similar benefit is the idea for electric aircraft is a similar benefit where you have significantly reduced emissions during use. And also much lower operating costs. So you don't have to now work with an engine manufacturer that requires engine overhauls and has oil and a ton of moving parts. It's really simple electric motors that are easy to replace if you need to. We're trying to not use any liquid cooling of anything either. So there's no cooling systems. It's all air cooled. And that's pretty interesting to folks who, for example, don't do cargo missions with normal helicopters for those reasons. They're too expensive and they don't want to be owning helicopters. This is kind of an interesting area for a lot of people. The cool thing about not working with an engine manufacturer is like now we don't have to work with the GEs or the Pratt and Whitneys or these huge companies, and where it takes usually for those companies, it takes about a decade to develop a new engine, where we can go and we can build our own electric motors in-house and have complete control of the aircraft as a small company. And that's enabled a lot of folks to get into this space. I think there's over 200 companies trying to do this right now. I'd like to think we're one of the leaders in that. But here's another few looks at other types of aircraft that people are developing, which shows that we don't really know still what the right configuration is. Everyone's trying different things. This top right one is a company in California called Joby. The guy who started this actually started, I don't know if you guys have seen the flexible camera grip Joby mounts, but he was the guy who invented that and made a bunch of money. And now he's trying to do an electric aircraft startup as well. So this plane has 6 propellers mounted kind of in a hex pattern, and they all tilt. So basically it takes off like a helicopter similar to ours, and then they all start to tilt forward, similar to the way an Osprey does. And that's how it transitions onto wing. The bottom left one here is a company called Archer, also in California. They're kind of in between our design and a Joby design, where some of their propellers tilt forward to get them onto wing and some of them stay stationary. And ours, I kind of talked about a little bit, but ours basically, these propellers hover, and then as you start getting a forward flight, they just kind of slow down and stop. So there's not a lot of tilting mechanisms involved. We think that reduces the complexity and ultimately makes it kind of a safer vehicle. This one in the center is kind of a funky one. It's a company called Lilium, and they're in Germany. And they've raised quite a bit of money as well. And they have, on their wings, they have these small ducted fans that basically pull air over the wing and basically increase the lift that the wing has on it as well. So yeah, it's kind of cool. It's kind of a new frontier of aviation, and people are trying to figure out what the best configuration is. And a lot of people have different ideas on how to do that. So yeah, like I said before, we're kind of just at the point now where the battery energy density is starting to make some of these helicopter type missions accessible for electric aircraft, which is why there's a ton of investment in the space right now. A lot of companies are going after basically an air taxi type market. So the idea is like in LA or other cities, you'd have a lot of these flying around, and they'd be much lower noise and safer than a traditional helicopter. So you can imagine basically an Uber electric aircraft type service that would get you from the airport into the city or something like that. For us, we're a little bit more focused on the cargo side. So we kind of think simple cargo operation is going to be an easier entry into the market. And it's kind of hard to imagine a lot of these brand new aircraft that have never been certified before, flying all over cities in the near term, especially with how slowly the FAA moves on certain things. So we're focusing a little bit more on cargo type missions for people like FedEx or UPS, where they do a lot of small flights of aircraft cargo, even from, like, for example, Plattsburgh to Burlington over the lake, where they'll bring a bunch of packages over, then they'll put them in a truck and bring them to a distribution center. And basically, the interesting thing about electric aircraft is that you can basically create a new mode of transportation. So you can actually take that short haul flight and that truck flight and combine it into one aircraft mission, and it basically creates a new mode in their transportation network to deliver stuff. The other cool customer we have is United Therapeutics. They're some of our first believers in us here in Vermont. The woman who runs the company, Martine Rothblatt, founded SiriusXM Radio, and then she founded United Therapeutics. Basically founded the company to save the life of her daughter, who had a health condition that there wasn't a cure at the time, and she did it. It's like pretty amazing, and she has a lot of really cool TED Talks. But the one thing they're working on right now, which is super exciting, is they're growing organs in pigs for transplant into people. So, what happens right now, if you need an organ transplant, you're on a really long wait list. A lot of people die waiting for organs. And you have to wait for something to happen, like people will die in a car accident, and then it's this rush to get an organ to the right place and make sure the person on transplant list gets there. And so they're basically, the idea that her company has, and they actually did one of the first, I think they did the first heart transplant this way. They're called xenotransplants, I think. They actually did one successfully this year down in Maryland. But basically the idea is you can basically grow organs in pigs, and now when you can do that and you can actually provide all these transplants to people and save their lives, you need ideally an environmentally friendly, low cost way to now transport these organs all over the country. So that was kind of her vision in this field. And she's a big lover of aviation too. And she's one of our big backers. And that kind of plays into our kind of cargo type mission of bringing high value cargo from distribution centers to hospitals and stuff like that. So the company, as I was saying, has grown quite a bit. Where in the beginning it was certainly a lot of engineers trying to get things to work, and now we've expanded quite a bit. I talked a lot about engineering, so I'm an engineer, but there's a ton of really, really valuable people here that keep things running. As a technician, for example, you can do a lot of hands-on work and hands-on technical work without necessarily having an engineering degree. So there's a picture in the top left here. These are a few of our, this is Malcolm, one of the composite techs we have here, working in the back of the aircraft, doing some repair on the side here. So you can, build things with carbon fiber. You can do welding. This is a close-up picture of one of our landing gear components. So this is inside the gear, and it's a welded machine part that takes a lot of the stress during landing. You can be a technician and run test operations. You can run motor tests and look at performance of motors and stuff like that. We also have a lot of pilots that basically can teach you how to fly. So that's one of the cool perks about Beta, is you can learn how to fly and get your pilot's license while you're here through a lot of pilots and instructors that we employ as well. My correction, Mr. Bang, is I'm not technically a pilot. I'm a student pilot. I haven't gone all the way and gotten my license yet. So we'll see. Maybe one day. It is a lot of work, but it's pretty fun getting up and flying in those small planes. But as we grow, we have all sorts of people working on communications. What is our web presence? How do we work with the local government? With Burlington, for example, on zoning of new buildings, if we want to build up manufacturing presence here. Certainly, folks, I talked a little bit about the program management side, but people who aren't necessarily doing the hands-on design engineering, but are trying to take a bigger picture about schedule and costs, and do we have enough people to do the things we want to do? And then a lot of HR in terms of hiring. We're trying to hire a lot to try to support certifications, having people that can go through resumes, find the right people, and work with the different teams to find those folks. Certainly finance and operations, making sure day-to-day stuff is working and projecting our finances and trying to organize all the fundraising around and stuff like that. And then, management of our facilities. We have multiple, we have our hangar here near the airport, and then we have a few manufacturing type facilities in the area. So managing all those, even simple things like making sure they get plowed in the morning. If there are leaks, making sure those get fixed, stuff like that. So we have one thing I didn't talk about is we design recharging pads for these things too, so they can land on top of basically heliport pads and then recharge the aircraft and go. So we have a lot of fabricators there, woodworkers, that design the interiors of those things and stuff. And then also just a few folks that are focused, as the company grows a lot, we want to keep the fun culture of the company going and not have it become one of these huge companies that a lot of us have left to join Beta. So there's a lot of focus on keeping it fun and making sure people don't get burned out, making sure we're well fed. We have a kitchen where we get lunch every day from our awesome meals team on the bottom right here, doing a Bohemian Rhapsody cover recreation and stuff like that. So it really takes a lot of people to run the company well outside of just engineering. So my job now, as the company's grown, I work as what's called the Flight Sciences team lead. So I lead a group of 5 people right now that work on what's called the flight sciences of the aircraft. So it's aerodynamics, performance of the aircraft, control, and stability. So it's making sure the aircraft is nice and smooth in the air, so it doesn't take a lot of power to push it forward. Making sure it's stable. So if the pilot gives a certain input, we want to make sure the aircraft doesn't get out of control and it kind of wants to return to nice level flight. Bottom left here is a picture. This is a simulation of one of our propellers. As you're moving forwards, the flow is coming from left to right. And there's a lot of complicated stuff that goes on in the propeller with the blades coming forward and backward in that flow regime. So we do a lot of work analyzing that with different tools to make sure we understand the forces, to make sure the aircraft can actually move through those different flight regimes. And our group, we end up generating basically a lot of requirements for the other groups. So we'll tell the motor team, hey, your motor has to be able to do this amount of power for this time so we can climb the aircraft up to altitude, for example. Or the tail needs to be this big because we want to be able to land with winds coming from this direction at this speed, and you need that much control authority to do that safely. And then the other thing we do on the top right, it's a little animation of the structural vibrations of the aircraft. So we have to look at, what are the natural frequencies of the aircraft and how much vibration do you see and how much is acceptable in flight. We have to make sure we can predict that all while accounting for example, the loads from the propeller and stuff like that and pilot inputs. So a few pictures here. The bottom right one is a picture from some of our flight tests. We have 2 prototypes right now, which we're flying, mostly flying like normal planes for right now and figuring out how all that works. And then we're getting back into doing the hovering kind of like a helicopter. And I think the room I'm in right now is a nice view of the hangar if you guys want to see it. So I think you can, so this is the hangar right to the left here. So you can see one of the aircraft right there. That's our serial number 1 aircraft. So we have 2 that we fly right now. This is the one we've been flying mostly. If you're ever up in Burlington, you might see it flying above the airport or over in Plattsburgh, but it's pretty cool to be, right near the hangar, right around the aircraft, and be able to go down and look at them whenever you want. This one, for example, yesterday we were looking at, we weren't getting the climb rates that we thought we wanted. So we kind of went around the aircraft and looked for ways we can increase or reduce drag and make it a little slippery in the air so we can climb faster. But yeah, that's one. And then back here, you can kind of see behind it is the second one. So that one we're doing some repair in the tail of it right now. We've found some defects in the manufacturing process on it recently. So we're going to get that fixed up. And then that one is primarily focused on hovering, more kind of like a helicopter. But you can see there's a lot of other planes in here. There's a lot of pilots that work here. So we end up buying other planes and they kind of help us, get a feel for what it's like to fly and how we can incorporate that knowledge into the design. But also we use them, for example, to ferry us over to Plattsburgh if we're doing flight testing over there. So I think the couple of small planes, the cool one, we have a stunt plane over in Plattsburgh, which is kind of sweet. And then there's a Husky that's not here, but we put skis on it in the winter so you can go out and land on the lake. And then in the summer it has floats, so you can go out and do the same thing. So, and a little helicopter in the back there too.
Riley, we probably have about 10 or 15 minutes. Can we open it up for some Q&A?
Yeah, definitely.
Yep. Anybody have some questions a question for Riley? I had one, going back to that kind of, it wasn't really an organizational chart, but you had a list of all the different kinds of roles at Beta. And one that struck my eye was within communications, you have storytelling and web presence and government relations. Do you guys create a lot of media? Do you use social media to get your story out there? Do you create video to kind of explain what you're doing at the company? And can you speak a little bit to that?
Yeah, we do. And we kind of, our strategy is we try not to be, you know, a lot of the companies, they'll have these really nice airbrush simulations of the aircraft flying to try to kind of help tell the story of how they work. But you know, a lot of those, it takes a lot of money to create those. And a lot of times it ends up making people feel like they don't really know what you've done or not. So, you know, our goal is to be pretty minimal in what we share. And when we do, share stuff, we'll share things that we're actually doing and actually flying. And I think that, I think honesty and straightforwardness and practicality has resonated with a lot of our investors. So we do have an Instagram account. I think we did just get a TikTok account recently for all you young guys out there. We do a little bit of it. And it is kind of interesting because if, you know, there's one of our board members was talking to us about this the other day. You know, if we want to be the practical heads down engineering company, like on one hand, you want to be humble, right? And that's like kind of what people I think like about us is we're just trying to build the product and we're not trying to do a lot of flashy PR stuff. But on the other hand, like you want the world to know that, you know, so you have to try to communicate the fact that you don't, that you're humble and you don't communicate all this flashy information about the company and oversell anything. And that's kind of the ground we try to navigate. So we do have you know, a website where there are a couple of really good YouTube videos about us and the culture here that are kind of cool to watch. But yeah, we don't do probably as much PR as some of our other competitors do.
Talking about like building electric aircraft, and like I know like if you have like an engine failure mid flight on like a normal aircraft, like the common procedures start needed, but like you have an electric aircraft, it's not as common just get the motor that's not working to start working again. So you kind of design that like in your process of like if this certain thing went wrong, you have procedures that maybe maximize your best flight and stuff like that.
Well,
yeah.
were you able to hear that?
Yeah, I think so. You're kind of talking about engine failures and how you design for those and other types of failures.
And the difference between an engine failure with an electric motor versus a gas motor or a typical motor.
Yeah. So that's actually a lot of the work our team does. And you know, a lot of the requirements from the FAA is you look at different failures and you look at the probability of those failures happening, and then you have to show what's going to happen and show that you can mitigate those with what's called continued safe flight and landing. So you don't have injury to people on board. So what we do on our plane is actually, you know, the engine failure thing is a huge one. And for each of these propellers in the corner, we actually have two motors in there. So we have two motors inside these booms, totally mechanically redundant, so that if one fails for some reason, the other one can actually continue to drive the propeller. So it's similar to like a multi-engine helicopter kind of in that sense, where you have two engines driving the same prime reliable shaft. But yeah, we look at that all the time. And you know, for different takeoff conditions, we have to look at that. The same thing with this, there's a certain amount of redundancy built into this pusher propeller, which also kind of helps in terms of the safety compared to a conventional engine. But yeah, you have to look at all that stuff, and even failures of things like the control surfaces. So these are the ailerons out here that help the aircraft roll. And then on the rudder, on the back, on the verticals, that helps the aircraft directionally control. So you have to look at what happens if any of those fail, like if you lose power to them or if they jam some way. You have to look at how does that affect handling? How does that affect handling if you're in a big crosswind, you know? And so we have to go through all these safety analyses, figure out what the critical failures are, and then actually do a lot of designing and sizing to those failure conditions as opposed to the normal operation conditions.
Go ahead, follow up.
Oh,
speak nice and loud though.
So you're also talking about your control systems and also are you guys using hydraulic controls or are you switching to just electric motors for like aileron and rudder?
Yeah, good question. It's all electric. So all the actuators on the wing are all servos. So they're just big, bulky servos. They're actually made by a company that makes big drone servos, basically. But everything's fully electric, what's called fly-by-wire in the industry. So no hydraulic lines or anything like that. And the smaller aircraft, it's all cables, right? It's all cable driven from the yoke, but this is all pure electronics, sensors that a stick up in the cockpit, and then it goes to all the surfaces and the motors.
Yep, Oliver?
All right. Do you think in the future, like all aircraft will be electric, or like how long do you think that will take?
Yeah, it's a good question, because if you do the math, on a big commercial aircraft in terms of, how much energy they can store in fuel versus how much energy a typical battery can store, you need like, I think it's like 1 million pounds of battery. You need some crazy amount of batteries. So I think like as the battery technology improves, we'll start to see migration of electric propulsion to larger aircraft. What's interesting though is there's a lot of hybrid options too that start to become viable much earlier than full electric options. So you can imagine a big, fixed wing aircraft like the size of a 737 that maybe has some electric propulsion that helps it during takeoff when you need a lot of power. And then when you go into cruise, that's when you rely primarily on your conventional fuel engine for long distances. So there's some really cool like games you can play in terms of how you manage your installed power. And there are certain, some of the work I did at my previous job, we were looking at big hybrid options like that. And they do start, as the battery energy density gets better, they do start to buy their way onto the aircraft in kind of interesting ways. So I think, in terms of pure electric, like if you think about the first electric cars that came out, right, they were useful in a very narrow sense. And I think that's where we are now in terms of these electric aircraft. They're going to have to be small. There's a fair amount of normal fixed wing electric aircraft startups as well right now that are like 9-seaters or something that are pretty cool. But I think as things grow, you'll start to see some hybrid options, or some companies like Airbus are still pretty committed to hydrogen fuels as well.
Thank you. Because if we hear a bell, or let's just stand here together, we'll dismiss you all together instead of people going exactly when the bell rings. Another question back there?
So you're talking about like getting things set up and like certified with FAA for flight, and I know they're not really like cooperative and helpful a lot of times. So I was wondering, is there any times where you've had like an idea that's been like pretty fleshed out and you had like stop or change something like drastically with the FAA?
Oh yeah, we're still doing that right now. Like it's, we still have a lot of technical challenges with proving that this works. We've done flight testing in certain regimes, but we haven't covered everything. And so we have some design changes we're looking at on the propellers, for example, where we're trying to reduce the amount of loads that go into the rest of the structure. And some of them do become pretty big architecture changes, but that's kind of the cool thing about being in a startup is we really try not to have a lot of mental inertia in terms of around a specific design. And if something is the right way to go, especially if it helps our customers in the end in terms of giving them more payload or more range, then we're going to do that. So yeah, absolutely. The landing gear, we had some pretty big configuration changes where, it used to be just a skid gear like a helicopter, and we now have wheels on it, which allows you to take off conventionally as well, which we think will be really helpful. So that was a big architecture change. Even now we're looking at resizing some of this stuff before we actually release the parts for the certified aircraft to try to help reduce drag and stuff. So.
Hey, Riley, we're going to have to end it, but I wanted to ask you one more question. You and I traded some emails last spring about some internship possibilities that you guys had at Beta. Is that a program that you will have again? Oh, there you go.
Yeah, totally. So we do internships every summer, and we also are doing a high school job shadow program now. I think this is the first time we're doing it, so it's a little bit of an experiment, but I think we're accepting applications for that now, and it'd basically be job shadowing through the summer for high schoolers. But on the internship side, usually we fill those kind of in the fall or winter timeframe, and it depends on, the different groups will have different needs in terms of experience level. But certainly we have high school interns sometimes that are down doing composites work or help build things or run tests and stuff like that. But the shadow program is kind of an interesting opportunity that we're still accepting applications for. You could come and just kind of follow around different engineers and understand what they do at the business.
Would you be able to share that presentation with me, and then I can get this information out to anybody who's interested?
Yep, sure thing.
And is the job shadow a single day or multiple days?
So I think it's a few hours a week through 8 weeks. So it's 8-week program, and then you come for a couple hours each week.
And is that specifically for engineering-minded students, or do they are there opportunities to spend time with people in other parts of the company?
I think it's throughout the whole company. I would have to check to see specifically what who's taking on who, but I think there's certainly roles, in the operations or the HR or the PR side as well. So definitely not just engineering.
Well, do you remember Best Thursdays when you were here?
Yeah, I do.
We're about to have a Best Wednesday in a few minutes. So that's what's up next for everybody here. I want to thank you so much for making the time and this was such a thoughtful presentation. So thanks for all the time you put into this presentation. It was great. And I'm thrilled that we were able to record it. So.
Yeah, no problem. And if you guys have any more questions, you can feel free to share my email with Mr. Bango, and you guys can reach out and ask anything you want.
Guys, can we have a round of applause for the audience? Hey man, thank you so much. That was awesome.
No problem. I hope I didn't take up too much time, but it sounds like we got some good questions in there. So.
Yeah, no, it was perfect. And again, I'm thrilled that we could record it.
Yeah, absolutely.
We have other students and certainly other teachers that were your teachers that would like to take a peek at it.
Yeah, that'd be great.
Okay. All right.
Thanks.
Cheers. Thanks a lot.